Our next section is on safety and operations, and our first speaker is Peter Shannon, who's the founder of Radius Capital. Peter is an investor focusing on transportation technologies with a current focus on advanced aerial mobility and its application toward positive impact for transportation across the economy. Peter's active in the aviation community around aerial mobility. He's an appointee to NASA's Aeronautics Research and Technology Roundtable through the National Academies. He's also helping to define a national vision and roadmap for UAM, also through the National Academies. Earlier, Peter was at Firelake Capital and Atlas Venture, investing in transportation and sustainability technologies. He holds an MBA from the University of Chicago Booth and a BS in Systems Engineering from the University of Virginia. He started flying when he was 19 and actively maintains a private pilot certificate with instrument rating. Please welcome Peter.
Thanks, Yolanka, for that very kind introduction. So this is actually my third year having an opportunity to speak at this event. And the first time I spoke here, I was just starting to look at this space and was coming up every learning curve you can imagine to understand how technology is beginning to impact flight and what the implications of that are going to be. Last year I spoke more about that and about the way that an investor looks at this set of opportunities and about the broader implications for how this technology is going to manifest solving different problems across the economy. And we've all been in this this broader conversation, thinking about, well, which are the technologies that come first? What are the business strategies that we can get started on right now? What is the sort of necessary order of deployment of these systems over time? What I'd like to talk about today is much more narrowly focused than what I've discussed in the past. And what we'll get into is the question of autonomy looms large across many of the types of systems that we want to deploy using new aerial mobility, whether for cargo drone logistics networks, for drones beyond visual line of sight, or for high-density urban air mobility. And I've gone to a lot of meetings around the question of what is it going to take for us to build this type of autonomy into air vehicles and into the airspace system. And I've heard a lot of the same questions posed, a lot of the issues relating to certification and to creating standards around this. And it's a very complex, very dynamic topic. There are a lot of programs across FAA, across NASA, and coming out of industry, and that's just in the United States around this. And what I think we can do today is we can distill that down and step back and try and understand some of the concepts that tie all of this together so that perhaps we can build a shared understanding of the issues around autonomy and a more clear set of expectations as to what we can think about in the next 5 years, the next 10 years, in terms of these systems actually being able to fly. So to begin with that, let's talk about the very key aspect of safety. I think that is clearly one of the biggest gates to us implementing increased levels of autonomy in air vehicles or in the airspace system, is to figure out how do we assure that these systems are going to be safe and that they're going to be reliable for the safety critical operations that we have in mind. So when we think about safety assurance, we can kind of break it down into two broad categories. One is operations safety assurance, which is what are the procedures in the airspace system that are safe. And in many cases, throughout the history of aviation in the United States, these operations safety has been derived from past experience. An accident happens, we learn from that accident, and we build procedures into the system that prevent that from happening again. And then we have this other aspect of design safety assurance, which falls in, certification falls into this category. This is understanding, are the systems that we build, Are they correct for the task, and are they reliable? So today, with respect to driving operations safety assurance into the system, one of the things that we depend upon a lot is training of human operators. We have pilots and air traffic controllers and others who are highly trained that make our airspace system work today. The operations safety assurance comes in the form of that training, and then the way that we do the design safety assurance for that is through the very familiar mechanism of licensing that verifies that the training is correct, and then it involves ongoing monitoring as well. And that works really well. As we next think about how we're going to move into a more automated system for any given function, we have to think, okay, well, how do operations safety assurance and design safety assurance manifest in this case? With operations safety, we're no longer training a human, but we have to define the process now in software. And that can be a very, very different process than the training, and it can lead to a big increase in the type of data that's required and a big increase in complexity. So for instance, if you want to build collision avoidance into an automated system, in today's airspace in VFR rules, we have a very well understood human definition of well clear. But if you want to implement that in software, how do you mathematically define what well clear is, and how do you build the data to support the implementation of a system that can do that? Likewise, for the design safety assurance, we have to verify and validate that that system that we've built is actually built to the right requirements and that it's indeed reliable. And doing that involves an increase of complexity as well, in that we need new techniques to figure out how do we assess this software and this hardware, how do we assess this system to understand that it is going to be reliable to the level that for its role in the system, we need to depend upon it for. And this happens function by function throughout the airspace system. And as we go forward, as we talk about building higher levels of autonomy into vehicles and into mobility systems, we have to look at this process playing out over and over again throughout different functions. Now, we've already done a lot of this in the past. So in the decades ago, where aircraft were, so we're talking about steam gauges and navigation and flight stability, and all of these things were the sole responsibility of the pilot. We still had design assurance and certification of the airframes and the propulsion systems. In recent decades, we've certified fly-by-wire systems, more advanced structures. We've seen with modern avionics and glass cockpits, the transfer of navigation and guidance responsibilities at a low level from the human pilot into systems that we designed and certified. And more recently also, we're doing this with collision avoidance, and in the process, taking collision avoidance to another level of scale and capability. Each time as we make these advancements, we're building new technologies that we need to figure out how do we define them from an operations safety standpoint, and how do we verify them that these systems that we design are indeed safe from a design safety assurance standpoint. As we go forward with even higher levels of automation in aircraft, we're moving the pilot further and further out of these inner control loops for the operation of the aircraft to more executive level functions, to these outer control loops. And as we move into this next phase of building situational awareness, the types of things that the pilot still does today, but automating those into aircraft that can be truly autonomous in their flight profiles, we have some fundamentally new technologies that we not only need to define, but we need to provide design assurance for. And in doing that, we really have some new tools and techniques that we need to develop, and ongoing research that needs to continue moving forward, in order to enable us to make that a tenable undertaking. Because as those of us in the business know, the development and certification of much of the software that goes into these systems is already an expensive and time-consuming task. As we bring in machine learning systems and different types of automation that look at large amounts of data streams, detect patterns in them, and take mitigating actions based upon risks that they detect, we're starting to introduce non-deterministic software into the avionics systems. And the design assurance of those systems is something that it's difficult to support with the current techniques that we use for certifying these systems, or for assessing, even if we're not going to certify them, for assessing what their level of reliability is. And there's ongoing work in that area that's continuing, and that's applicable to what's going on in the aircraft as well as in the broader airspace system, which we'll talk about in a moment. For most of the operations that we're flying today in commercial aviation and general aviation, the procedures are really well understood. And so the definition of the operational safety is derived from our understanding and experience from how we've been flying in recent years. Going forward, as we're building new types of vehicles and we're employing them in new applications, which is one of the great opportunities with all of this new technology coming into aerial mobility, we need ways to assess and create and define new operating procedures that we can, from the beginning, understand have a high probability of being very, very safe. So we're not going to be taking a forensic approach, learning from past accidents in order to drive safety into our operations, but we're instead going to need to be able to do that with data, and we're going to need to be able to do that up front. So as we again look at this idea of inner control loops moving to outer control loops, and we look not just at what we've done in driving autonomy into an individual aircraft, but we begin to look at it across a full airspace system. So an aircraft operating in a broader system that includes air traffic control and all of the other aspects, we see a similar pattern unfolding. We go from surveillance that was primarily radar-based to surveillance that is multimodal. We have satellite navigation, we have other types of communications, and we have new types of radar and other surveillance that are being planned or introduced that need to be incorporated into this system. We have a big hurdle in terms of, if we want to drive scale in these operations, probably the crux of this problem is figuring out how we drive higher scale in air traffic management. And this isn't about automating it entirely. Humans are still in the loop in this. But in order to drive that scale, there is a lot of data that we need to collect and fuse on a regional level in a sort of a geospatially aware, near real-time type of system. And there's a lot of processing that needs to sit on top of that, incorporating these different types of data in order to detect situations, high-risk states, and then immediately advise on ways to resolve that. One of the questions that is unfolding as sort of another dimension in this is, when these systems are built and fielded, are they going to be certified, or are they going to be sitting separate from that? In other words, there's an ongoing question right now as to which parts of this system are the safety critical backstop, and which parts of this system that do need to be certified, and which parts of the system are the other pieces of the operation that, while intended to be reliable, are not necessarily the final safety critical backstop upon which you do the certification. Developing the experience with operations and the data and clarity around this question is sort of a key sort of intersection to what's going on in this technology development. So we understand for what types of applications Are we going to have to certify air traffic management or the supporting systems? And for what types of applications is that not necessary? And the vehicles themselves are what get certified because they have their own internal capabilities to, as a backstop, provide that level of safety. With air traffic management being the crux, we have a set of technologies that are going to be developed around bringing higher levels of scale to the broader airspace system, automating levels of routing and planning, incorporating the data around the status of ground infrastructure right alongside the situational picture of what's going on in the airspace itself, and bringing that up to a level where we are able to, in an automated way, look at risk factors across vehicle maintenance issues, across weather, across traffic, and drive this type, these types of safety requirements, drive this level of safety in a scaling system that has emerging applications, a flexible system that may be supporting types of flight operations that we don't have yet, have a lot of experience with today. There is a need for us to build a generalized system that can accommodate this flexibility while giving us the data in which to be able to measure the safety levels that it can provide. Again, on the design safety assurance level, we see some of the same tools and techniques that we built in enabling us to certify these types of automated systems in an aircraft being needed and being applied to assuring the safety of these systems in the broader airspace system. And on the operations side, it becomes more of a question that is not derived from past experience with commercial aviation or general aviation applications, but rather these are a drone delivery network or new high-scale automated flight operations. We need a data architecture that allows us to capture and characterize that and then understand the best operational procedures and practices in order to assure the safety of those systems going forward. So when we think about this roadmap for building autonomy into our flight operations, we see that there are some core concepts around how you go about thinking with regard to safety assurance, and that there are some foundational technologies that we've made a lot of progress on building, but we have a lot of additional research to do, and we have a lot of decisions at a policy level to make in terms of the architecture of how this system is going to be built. One of the important things that it is tied to making those architectural decisions is that when we have the type of clarity around how are secure communications going to work in this system, how is data going to be shared across these different sensors, how is the architecture for detecting and mitigating risks in this system, what are the baseline standards and protocols for doing that? When we have built that foundation and made those decisions, we're going to be able to unlock a lot of activity in the private sector because they will be able to invest and commercialize their innovations with the confidence of knowing how it's going to plug into this broader architecture. And that's a really important takeaway from this, is to understand the path we have ahead of us, the task that we have to characterize this system and understand its safety, the questions we have around which pieces of this system need to be certified in the legal sense, and which pieces of this system we need to understand the safety assurance of from a more operational sense, and then have the ability to build an airspace system that can scale in the ways that we want it to by orders of magnitude in terms of activity, but also have built into it the type of flexibility for the numerous new applications of flight that each of us with the different businesses that we're pursuing, that each of us anticipate trying to be able to commercialize and make fly. And I already covered this, which is the idea of a generalized architecture for doing this. So this is, clearly, we know this is a complex roadmap ahead of us. We need to have reasonable expectations in terms of the timing of when we think different pieces of this are going to come together. And when we also need to think about, well, with respect to certain pieces of it, what flight operations can we enable and can we get going in the next 3 years, the next 5 years, the next 10 years, based on a more clear understanding of what it means to build autonomy in a safety-assured way into our airspace system. I'll stop there.